Okay, there we go. So let me first introduce the three trigonometric functions, sine, cosine, and tangent. So basically sine is when you have a triangle. Let's say you have a right triangle, A, B, C. And B is a 90-degree angle. And let's denote angle C as alpha. Then if we say sine of alpha, then this will be equal to the length that is opposite the angle alpha, which is AB, divided by the length that is the hypotenuse of the right triangle, which is AC. And this is the definition of sine for an angle in a right triangle. And similarly, we have cosine, which is commonly written as COS. And this value is equal to the side length that is adjacent to the angle alpha, but not the hypotenuse. So that would be BC. And once again, we divide that by the hypotenuse AC. And finally, we have tangent. And tangent is the function equal to sine divided by cosine. Sine of alpha divided by cosine of alpha. So if we divide these two, that's equal to AB over AC divided by BC over AC. And this will just give us AB over BC. So this tells us that tangent is defined as the leg that is opposite of the angle alpha, which is AB, divided by the leg that is tangent to the angle alpha, which is BC. And these are your three most basic trigonometric functions. And so these expressions have values. So let's say AB was 3, BC was 4, and AC was 5. It's a standard 3, 4, 5 right triangle. Then sine would be 3 over 5, cosine would be 4 over 5, and tangent would be 3 over 4. And that's only of this particular angle alpha. If we have this angle right here, BAC, which we will denote beta, then the sines, cosines, and tangents will be different from that of angle alpha. Think of it as a function, and depending on the angle that you plug into the function, the value will change. Obviously, that's not always the case, and we'll talk about how these functions are periodic later. But for the most part, if you plug in two different numbers into sine, you'll probably get different values. So quickly, let's just calculate the three trigonometric functions for beta. So let's say sine of beta, that's equal to the opposite of it, which is 4, divided by the length of the hypotenuse, which is 5. And then cosine of beta, is equal to the length that is adjacent to beta, which is 3, divided by the hypotenuse, which is 5. And tangent, oops, my pen's messing up, sorry. Tangent of beta is equal to the length opposite of it, which is 4, over the leg that is adjacent to it, which is 3. So this is just a very brief introduction to sine, cosine, and tangent. And let's move on, let's talk about these values for specific angles. So let's consider a 45, 45, 90 right triangle. I'll try to draw it as, oh my God, that's not very good. Let's say this is a 45, 45, 90. This is 45, this is 45. And then we also have a 30, 60, 90 right triangle, which is another very common triangle that appears in math. And the larger angle here will be 60. The smaller angle here will be 30. And let's try and compute the trigonometric values for these angles. So let's first consider this 45-degree angle. Or rather, before even that, let's talk about the side lengths. Since these side lengths are all I guess, arbitrary values, we can just assign this as 1. And since 45, 45, 90, that's an isosceles triangle. That means that this other side length will also be 1. In fact, we can denote just A, B, C for the sake of simplicity. So AB is equal to BC because angle BAC is equal to angle BCA, which is equal to 45 degrees. And now we can use Pythagorean theorem to find out that AC is equal to square root of 1 squared plus 1 squared, which is just square root of 2. So then if we calculate sine of 45 degrees, this is just equal to the length which is opposite of it, which is 1. And we divide that by the hypotenuse, which is root 2. And if we rationalize this, this is just root 2 over 2. Now we can also take the cosine of it, but you'll find that it's actually the same thing because the side length that is adjacent to the 45-degree angle is equal to the side length that is opposite of it. So this is also 1 over root 2. It's root 2 over 2. And finally, we have the tangent. And let me move the screen down a bit. We have the tangent. And the tangent of these two values is just, of this value, I mean, is just 1 because we have 1 divided by 1. So the 45-degree angle, that's actually a very common angle that you'll see in sine, cosine when dealing with trig in general. So it's really good to memorize these values. And if you find yourself forgetting, you can always just draw this 45, 45, 90 right triangle and derive the values yourself. And next, let's move on to this 30, 60, 90 right triangle. So I guess let's just assign this value as 1, this length. And let's once again assign 3 points, A, B, C. So we arbitrarily assign BC to be equal to 1. And in a 30, 60, 90 right triangle, we have that AC has a length of 2 and AB has a length of root 3. So then let's talk about the trig values. So let's first start with this 30-degree angle. So if we have sine of 30, that's equal to the angle, the length opposite it, which is 1, divided by the hypotenuse, which is 2. So that's just 1/2. If we have the cosine of it, that's equal to root 3 over 2, since the length adjacent to it is root 3 and the hypotenuse is 2. And finally, the tangent of 30. Tangent of 30 is equal to just the opposite over the adjacent, which is 1 over root 3, which we can rationalize as root 3 over 3. And similarly, let's talk about 60, the 60-degree angle. So sine of 60, I think you guys get the hang of this by now. So let me just move a bit faster. Oops. Cosine of 60 is just 1 over 2. And tangent of 60 is equal to root 3. And you might start to see that this value right here corresponds to this value right here. And this value right here corresponds to this value right here. And basically, this is not a coincidence. You also see that with the above example in the 3, 4, 5 right triangle. But the reason for this, which I guess I'll go into more depth later, is for the simple fact that we have this formula, which sine of an angle x is equal to the cosine of 90 minus x. So basically, if we have sine of 60 where x is equal to 60, then we have that sine of 60 is equal to cosine of 30. which is exactly what you see here. So this formula also works the other way around. So like cosine of x is equal to sine of 90 minus x. But that's the general one you have to keep in mind, basically. And so moving on, there's two more important angles that have trigonometric values that are important, I guess. So first we talked about 45-degree angle. Then we talked about the 30 and 60-degree angle. Now let's talk about the 0 and 90-degree angle. So in short, there's no good way to measure it in a right triangle, but basically we have that the sine of 0 degrees, that's equal to 0. The cosine of 0 degrees is equal to 1. And the tangent of 0 degrees, it's equal to the sine divided by the cosine, 0 divided by 1, which is still 0. Now talking about 90 degrees, we have sine of 90. That's equal to 1. Cosine of 90 is equal to 0. Again, know how these values are the same. And finally, we have tangent of 90, which is 1 over 0, which is undefined. So the reason that we can find this 0 value and the 90-degree value is because we can look at something called the unit circle. So the unit circle is basically, as its name suggests, it is a circle of radius 1. So let me draw it out. It's be a very crude drawing, but that's not bad. So again, the radius of this is 1. So that here is 1. This is also 1. And the x-axis will be cosine, or basically the x-axis will be cosine of alpha, and the y-axis will be sine of alpha. And alpha is referring to the angle that is made by a length from protruding from the origin, and the angle it makes with the x-axis. So basically this angle right here would be alpha. And also similarly, if we had this angle right here, or not that angle, I meant this length right here, then that means this whole length would also be alpha. And so basically, let me go ahead and erase these. Basically, let's say if we have this right triangle, and that means this hypotenuse is equal to 1, since it's essentially a radius of the unit circle, which has radius 1. And also, this is alpha. And since we know that the x-axis is cosine of alpha, then that means this value right here is cosine of alpha, comma 0. And since the y-axis represents sine of alpha, then this value, I guess, let me just draw a dash line right here. This value right here is 0, comma sine alpha. So that means this point where they meet is equal to cosine of alpha, comma sine of alpha. And this concept may be a little confusing at first, I say, but basically this is important in recognizing how these angles are derived, I guess. So let's say we have let's use an example. Let's say we have alpha is equal to 3 degrees. This is an angle we talked about previously. So if alpha is equal to 30, then this point would be equal to root 3 over 2, comma 1 over 2. And that is because cosine of 30 degrees is equal to root 3 over 2, and sine of 30 degrees is equal to 1 over 2. So if we just plug these into cosine of alpha, comma sine of alpha, we get the corresponding point on the unit circle. And similarly, that just means that this leg has length root 3 over 2, and the vertical leg has length 1 over 2. And again, this is a right triangle, so we can confirm that if we add the squares of these lengths, so root 3 over 2 squared plus 1 over 2 squared, we do indeed get 1 squared, which makes this a valid right triangle. So what can we do with this unit circle, I guess? Well, basically, the first reason I mentioned it was in order to find sine of 0, cosine of 0, sine of 90, cosine of 90. So let's move the screen down a bit, I guess. I'll draw a new one since that one's getting a little messy. If we want to find sine of 0, cosine of 0, that means that alpha has to equal 0, which means that the angle between the radius that is formed with this part of the x-axis right here has to be 0. So that means essentially we have a quote-unquote infinitely small right triangle that is basically just like that. It's just a line. And since this length has 0 degrees between itself and the x-axis as a whole, that means this point right here will have exactly we'll have the value cosine 0, sine 0. But again, this is a unit circle, and if we have this plane, then that means this point right here is also equal to 1, 0. So therefore, we have that cosine of 0 is equal to 1, and sine of 0 is equal to 0. And similarly, let's talk about the 90-degree angle. So if we have this length right here, this creates a 90-degree angle with the x-axis. So that means that the point up here will have a value of cosine of 90, sine of 90. However, this value is also equal to 0, 1, which means that cosine of 90 is equal to 0, and sine of 90 is equal to 1. And also, let me tie in tangent to all of these. So going back to our triangle before, tangent is still basically the ratio of the vertical length to the horizontal length. So I guess there's no clear way to depict tangent in this, but if we have like a 45-degree angle, then tangent of 45 would obviously be 1, because the ratio of the vertical length to the horizontal length is 1, because they're the same length. So now that we have this unit circle, we can notice some, I guess, overarching observations. So let's say we have, let me once again draw another unit circle. Let's say we have these two angles. We can say that this one is x, and this small angle here is also x, but that means that this big angle here is 180 minus x. Let me write in green actually. Hopefully that makes sense, because we just drew two corresponding angles, and since this entire top half is 180 degrees, the remaining portion is 180 minus x. So that means that this value right here is cosine of x, comma sine of x. And this value right here is cosine of 180 minus x. Oops. Cosine of 180 minus x, comma, sine of 180 minus x. So that's the value of this point. And so basically, by, I guess, symmetry, you realize that this triangle here and this triangle here are exactly the same because they both have an angle of x. They both have a right angle. So that means that their legs must have the same length, as in this leg is equal to this leg, and also this leg is equal to this leg. So what does that mean for us? Well, basically that tells us that sine of x Okay, basically since these two vertical lengths are the same, that tells us that sine of x is equal to sine of 180 minus x. And also, if we notice that this length going in the positive x direction is equal to this length going the negative x direction, then that means that cosine of x is equal to negative of cosine 180 minus x. And again, the reason that we have the negative there is because one of these is going in the negative direction while the other length is going in the positive direction. Because we have to once again remember that this is a plane and everything on the right side is positive x, left side is negative x. And the same goes with top and bottom. The top side is positive y, the bottom side is negative y. So we have these two formulas right here, I guess. And you can see how they're derived by using the unit circle. So let me move on and let me introduce three more trig functions. And these are going to be secant, cosecant, and cotangent. So we have cosecant, which is denoted CSC. And this is function, or you write cosecant of alpha. This is equal to 1 over sine of alpha. And now secant of alpha is equal to 1 over cosine of alpha. And finally, we have cotangent. And this is equal to 1 over tangent of alpha. So these are our three, I guess, secondary trig functions. And we can, I guess, explore the value. So let's say we have cosecant of 30 degrees. Why is it not writing? Okay, there we go. Cosecant of 30 degrees, that's equal to 1 over sine of 30 degrees. However, sine of 30 degrees is just 1/2. So cosecant of 30 degrees is equal to 2. Similarly, if we have secant of 30 degrees, this is equal to 1 over cosine of 30 degrees, which is 1 over root 3 over 2, which is 2 over root 3. And finally, we have cotangent of 30 degrees. This is equal to 1 over tangent, and the tangent was 1 over root 3. So the cotangent of 30 degrees is just root 3. So with these three intermediate functions, they provide, I guess, they provide more flexibility we have, and also they introduce a few new formulas into our repertoire, which I'll go into a bit later. For now, let's talk about graphing. So returning back to the original three trigonometric functions for a second, we can plot them on a graph that sort of looks like this. This is going to be different from the unit circle graph. Oops, let me redraw that. Or actually, before I do this, let me introduce the concept of radians. So in case you don't know by now, 1 radian, or rather pi radians, is equivalent to 180 degrees. And degrees is the measure of angle that we've been always using so far in this lesson. Like I've referred to things as 30 degrees, or 60 degrees, or 90 degrees. However, these can all be translated into radians. If pi radians is equal to 180 degrees, then 30 over 180, that's equal to 1/6. So that means that 30 degrees is equal to 1/6, or sorry, not 1/6, pi over 6 radians. Similarly, 60 degrees is equal to, well, we can just double this 30 degree value times 2, and that gives us pi over 3 radians. And 90 degrees is equal to pi over 2 radians. And 180 degrees is just equal to pi radians. And like you can do this so on and so forth. So basically 360 degrees is 2 pi, 720, 4 pi, and so on. So that's just the notation I wanted to share before we proceed into the graphs. So returning back here, we can let this x-axis be the angle, and this y-axis will be the sine of said angle, which we'll say alpha for now. So we can start to plot this on a graph. So we'll start at alpha is equal to 0. Sine of 0 is equal to 1. And now let's plot the point at 180 degrees, or pi. So this is going to be pi right here. And sine of pi is equal to, or wait, I'm sorry. Hold on. Let me start over. Sine of 0 is 0. Sine of pi is also 0, because once again, referring back to our unit circle, sine is the vertical value. So at 0 degrees, it's 0. And at pi degrees, it's also 0. So when will it be equal to not 0? Well, basically when it's at pi over 2 degrees, it's equal to 1. So we can denote this value up here as 1. This is pi over 2. And so far we have these 3 points. And we can also plot intermediate points along the way. So if we have, this is pi over 4, sine of pi over 4 is root 2 over 2, which is going to be something here, let's say. And similarly for 3 pi over 4, it's going to be around here. We can continue on plotting. Let's say we can plot 2 pi, which is here. Sine of 2 pi, that's just a full circle around. So if we go a full circle around, we return back to having sine being equal to 0. So we can plot this point. We can plot the point in between them, which is 3 pi over 2. If we have 3 pi over 2, then that's down here, which is 270 degrees. And this is equal to -1. So if we have -1 down here. So we can start to see this sort of take shape. We can also plot to the left of the x-axis. So if we have negative pi basically means we go pi degrees in the opposite direction. So instead of going counterclockwise, we go clockwise. So if we go clockwise by pi, we reach this point again, in which the value is again 0. And basically, we can start to see this plot look something like this. And that's going to be the plot of sine. And I guess I can continue it. It's basically this wavy thing that continues on infinitely. This is actually a bit higher. But it continues on infinitely. And this is what I was talking about, that sine is a periodic function. So basically, for every value of x, this is equal to sine of 360 plus x. Or if we write in radians, this is equal to sine 2 pi plus x. Because it will always just shift it 2 pi to the right. So let's say we have this value right here, pi over 4. If we add 2 pi to it, that's 9 pi over 4. And that'll bring us right here. And it's actually the same exact value. Similarly, we draw that. Basically, these points all correspond to the same point 2 pi ahead of itself in this graph. We can also move backwards. So for example, these points are equal. These points are all equal as well. So basically, that just tells us that sine has no real, it has an unbounded domain. However, we can also realize that the range of sine is from -1 to 1. Because as you see from this graph, none of the points actually ever go past -1 and 1. They're bounded infinitely in between these two lines, right? And each of these peaks is supposed to touch this line. My drawing's just a little bad, sorry. So I guess I'll write it down. The domain of sine is -infinity to infinity. However, the range is from -1 to 1 only. Next, let's talk about the graph of cosine. So cosine is going to be a similar looking graph. If we start by plotting the points, we can see that cosine of 0 is 1. So we'll plot that here. That's 1. Cosine of pi over 2, that's 0. So I guess we can plot that here. Cosine of pi is -1. So we'll plot that down here. And this is pi over 2 pi. Cosine of 3 pi over 2 is once again 0. Cosine of 2 pi is once again 1. So this will be 2 pi. So cosine will look something like this. So it's similar to sine, but you'll notice that it's essentially been shifted to the right by pi over 2. Because sine would look like this. So you can see that it's basically, it's just shifted. So the graph of cosine is very similar to the graph of sine in that the range of it is unbounded. It's from negative infinity to infinity. And also the domain of it is from negative infinity to infinity. And the range is from -1 to 1. So let's talk about the final graph. There's obviously a lot more graphs for like secant, cosecant, cotangent, but we won't be talking about this today. So let's go ahead and mention the graph of tangent. The graph of tangent is very weird because we have to remember that tangent has a lot of undefined values. So for example, at pi over 2, tangent there is undefined because we have sine pi over 2 is equal to 1, but cosine of pi over 2 is equal to 0. So therefore tangent is 1 over 0, which is undefined. And the same can be said about 3 pi over 2. At 3 pi over 2, we have sine equal to -1, cosine is equal to 0. So this is also, the tangent is also undefined. And this in fact will happen for every value of pi over 2 plus k pi, where k is any arbitrary integer. So for example, 5 pi over 2, negative pi over 2, negative 3 pi over 2, so on. But for all of those values, tangent will essentially be undefined. So when we first draw our graph of tangent, we have to keep that in mind. So if we have this value can be pi over 2. This value can be 3 pi over 2. This value can be 5 pi over 2. This value will be negative pi over 2. This will be negative 3 pi over 2. So for each of these values, the tangent function is undefined. So we're going to mark it with a dotted line. Well, that didn't really pass through, but you get the point. So let's begin plotting. So tangent of 0, that's equal to 0. Tangent of pi over 4 is equal to 1. Have this be 1. Tangent of, I guess, let's say 60 degrees, that's equal to root 3. So if we have, wait, sorry, give me 1 second. We have tangent of, wait, hold on, I think I messed up. Oh, no, never mind. Basically, if we have -1 here, 3 pi over 4, tangent of negative pi over 4 will be down here. Tangent of pi over 3, which is 60 degrees, that's root 3. So that'll be a bit higher than that. And similarly, we have tangent of pi over 6, which is 30 degrees, and that's 1 over root 3, which is going to be like here. And for each of these values, we can plot them below to the left of the x-axis as well, because the values are simply negated. And we're going to end up with something that looks like this. Or let me redraw that. That's also not very good. It's kind of hard to draw graphs. Oops. Kind of like that. And basically this function, or this little or I can't even call it it's like a cubic. It looks like a cubic function. This will repeat itself between every interval of dotted green lines. So basically, it'll be there, it'll be there, it'll be there, it'll be there. And basically, this is the graph of tangent. It increases towards infinity as it approaches each value of pi over 2, and it decreases towards negative infinity when it approaches the multiples of pi over 2 from the left side. So yeah, basically these graphs here, they extend along forever, but they never reach the dotted green lines because those values are undefined. So this is the graph of tangent. It's very weird as opposed to the other graphs, but it essentially repeats itself within intervals of pi, because the width of this interval is pi, the width of this interval is pi, the width of each of these intervals is basically pi. Okay, now let's talk about the formulas involving secant and tangent and cotangent I was talked about earlier. Sorry, give me a second. Right. So let's say we have these are sort of called, I guess, the Pythagorean identities, you could say. I don't know if that's an accurate or like a widely accepted definition, but some people call it that. And basically, these are very important to trig, especially the first one I'm about to tell you. And this one is sine squared of alpha plus cosine squared alpha is equal to 1. And when I write sine squared of alpha, this basically just means sine of alpha squared. It's just we put the squared by the sine, so we don't accidentally try to write sine of alpha squared, because that's a little ambiguous. So, and then the ones involving tangent and secant, we have tangent squared alpha plus 1 is equal to secant squared alpha. We also have similarly 1 plus cotangent squared is equal to cosecant squared alpha. And I guess I'll go ahead and tell you why the first one is true. The first one, you can see that it's true from the unit circle. So remember we had something like this, where you had a right triangle. This vertical length is equal to sine of alpha. This horizontal length is cosine of alpha. And this radius of the circle is 1. So from Pythagorean theorem, you can straight up just see that sine squared of alpha plus cosine squared of alpha is equal to 1 by Pythag. And these three are basically really important identities to keep in mind, especially the first one. I guess you could get away with probably not knowing the second one, since secant and cosecant don't show up as much in problems, but the first one is absolutely crucial to memorize. As if you didn't realize by now, trig is a field which is very memorization heavy, I guess. But if you know how stuff is derived, then that can make the job a lot simpler for you. So I'm going to go ahead and talk about 3 last formulas for today, or actually 4. 4 last sets of formulas for today before we end off. And the first is going to be, I guess, the sum formulas. So that's what you get when you have something like sine A sine A plus B. So if we have sine alpha plus beta, let me make sure I have this right actually. I think it's equal to sine alpha times cosine beta plus cosine alpha times sine beta. And this is the formula for when you have sine of the angle alpha plus beta. So if you had something like, let's say you wanted to calculate sine of 75 degrees. This is equal to sine of 45 plus 30. So according to the formula, this would be sine 45 times cosine 30 plus cosine 45 times sine 30. So this is root 2 over 2 times root 3 over 2 plus root 2 over 2 times 1/2. So this is root 6 plus root 2 over 4. Just from this formula alone, we can calculate a lot of various intermediate trigonometric angles that are outside of the normal ones you memorize, which are 30, 45, 60, 90, 0. So similarly, if we have sine of alpha minus beta, that's basically the exact same thing, except we just replace, if we have minus, we just replace this plus with a minus as well. And that's that. Now let's talk about cosine. So if you have cosine oops, of, why is the writing so bad all of a sudden? Hold on. If we have cosine alpha plus beta, this is equal to cosine alpha times cosine beta minus sine alpha sine beta. I think that's right. That should be right. So basically for this one, you just have all the cosines at the front, all the sines in the back, and the sine is or rather the operation you is the opposite of the one that's in the original calculation. So if we had instead cosine alpha minus beta, this will become a plus. And finally, we'll talk about tangent. So if we have tangent alpha plus beta, this is equal to tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. This is probably, I guess, the hardest to memorize out of the 3, or maybe not, depending on who you are. But if you have tangent alpha minus beta instead, this would become a negative, this would become a plus. So those are the 3 sum and difference formulas, I guess. And from these, we're going to derive the double angle formulas. So the double angle formulas are basically formulas that include, or that find the value of sine of 2 alpha sine of 2 alpha, cosine of 2 alpha, and tangent of 2 alpha. And while these formulas, I guess, should be memorized in order to increase speed, if you can't memorize them, then you can just derive them from the 3 formulas above, like we're going to do now. So if we have sine of 2 alpha, this is just sine of alpha plus alpha. So according to the formula above, this is just sine alpha cosine alpha plus cosine alpha sine alpha. And these two terms are the same by the commutative property. So this is just 2 sine alpha cosine alpha. And that's the sine 2 alpha formula. Let me move these down. Oops. Let me do cosine 2 alpha down here. So cosine of 2 alpha, that's going to be equal to cosine alpha times cosine alpha minus sine alpha times sine alpha. This is equal to cosine squared alpha minus sine squared alpha. And if we use the property that sine squared alpha plus cosine squared alpha equals 1, then that means that cosine squared alpha is equal to 1 minus sine squared alpha. So if we plug that into this equation, that's 1 minus sine squared alpha minus sine squared alpha, which is equal to 1 minus 2 sine squared alpha. So that's another form to write it in. Let me circle. So this is the first form. This is the second form. And these three are all equivalent expressions for cosine of 2 alpha. And also there's one last form. So from this equation again, we get that sine squared alpha. This time we're going to move the cosine squared alpha to the other side, which is equal to 1 minus cosine squared alpha. So if we plug this in to this original green equation right here, this is equal to cosine squared alpha minus 1 minus cosine squared alpha, which is equal to 2 cosine squared alpha minus 1. So this is our third and final form for cosine of 2 alpha. Now finally we'll talk about tangent of 2 alpha. Tangent of 2 alpha is just tangent alpha plus alpha, which if we plug into our formula from before, this is equal to tangent alpha plus tangent alpha over 1 minus tangent alpha times tangent alpha. So product. So this is 2 tangent alpha. Oops, my pen's messing up. Sorry. 2 tangent alpha over 1 minus tangent squared alpha. And this is the formula for double tangent formula. So now we have our 3 double angle formulas. And like I said, you don't have to memorize these, it's recommended, but you can always derive them from the sum and product or sum and difference formulas we talked about earlier. So yeah, I think that's all I actually had to talk about today. So I don't have any questions. I got one question. What app am I using? That's the one I'm writing on is called OneNote, Microsoft OneNote. But yeah, that's gonna be everything I have for today. Thank you all for coming. The first time I did I guess I did or let me stop the recording actually.